In 1998, inside a conference room at Case Western Reserve University, a group of cosmologists sat staring at a set of numbers that should not have existed. The data came from distant exploding stars called supernovae, ancient light arriving from galaxies billions of light years away. The expectation was simple. Gravity should be slowing the expansion of the universe over time, but the numbers showed the opposite. The universe was accelerating. Something invisible was pushing space itself apart. At first, many scientists assumed there had to be an error somewhere in the calculations, but the measurements kept returning the same result. And hidden inside the equations was an even stranger problem. The value driving this acceleration appeared calibrated with impossible precision, balanced so delicately that even a tiny change would have prevented stars, galaxies, planets, and human beings from ever existing at all. There was only one major framework in physics that had predicted a universe like this before the observations arrived: a multiverse. At the same time, another branch of physics had already reached its own disturbing conclusion: quantum mechanics. The theory governing every particle in existence appeared to imply that every possible outcome of reality actually happens somewhere, not metaphorically, physically. And then cosmologists discovered something else: a gigantic cold region in the oldest light in the universe, a scar so large and so statistically improbable that some researchers proposed our universe may have collided with another one long ago. Three separate fields of physics, three separate paths, all pointing toward the same possibility: that our universe may not be alone. Quick favor before we continue. If you find yourself coming back to videos like these, hit subscribe so you don't miss the next one. It makes a bigger difference than you might think. To understand this, we need to go back to the physicist who asked the one question quantum mechanics never wanted answered. Imagine standing on a shoreline at night, watching black water disappear beyond the horizon. You know the ocean continues. You simply cannot see farther. Cosmology begins with the same limitation. When we look into space, we are not looking across distance alone. We are looking backward through time. Light moves at roughly 186,000 miles per second, fast enough to circle Earth 7 times in a single second. Yet the universe is so vast that even light arrives late. The glow from the Andromeda Galaxy began its journey more than 2 million years ago, before human civilization existed in any recognizable form. This creates a boundary around us. Physicists call it the observable universe, the region from which light has had enough time to reach Earth since the Big Bang began, approximately 13.8 billion years ago. That visible sphere stretches about 93 billion light years across today, because space itself expanded while the light traveled. Inside it sit an estimated 2 trillion galaxies, each carrying billions or even trillions of stars. But that sphere is not the edge of reality. It is only the edge of visibility. Beyond it, space almost certainly continues, quietly, indefinitely. Modern cosmology strongly suggests the larger universe extends far past anything we will ever observe directly. The horizon exists because light has a finite speed, not because the cosmos ends there. And this is where language starts causing trouble. When physicists say universe, they may mean several completely different things without stopping to clarify. Sometimes they mean the observable universe, the small illuminated patch we can measure. Sometimes they mean the entire spacetime region connected to ours, including areas forever beyond observation. Sometimes they mean a separate universe entirely, disconnected from our own spacetime, like an island cut off from every sea route. And sometimes they mean the multiverse, the total collection of all universes that exist, whether connected or isolated. These definitions overlap constantly. You can hear two scientists use the same word while describing radically different realities, but another idea matters even more for what follows: physical constants. These are the fixed numerical values woven into the laws of nature. They determine how strongly gravity pulls, how electromagnetism binds atoms together, how stars ignite, how quickly particles decay, and how light itself behaves in empty space. There are about 26 known constants in modern physics: the mass of the electron, the strength of the strong nuclear force, the cosmological constant tied to dark energy. What unsettles physicists is not merely that these numbers exist, it is that they appear chosen. No deeper theory has successfully explained why the constants possess these exact values instead of others. Scientists measured them experimentally because the equations alone could not derive them. Change even one slightly, and matter destabilizes, stars fail to form, or the universe expands too quickly for galaxies to emerge. The deeper researchers looked, the stranger this became, because the laws of reality did not merely permit complexity, they seemed balanced for it. In the winter of 1954, deep inside Princeton University, Hugh Everett III sat alone with equations that already terrified most physicists alive. He was 24 years old, quiet, brilliant, and increasingly disturbed by what quantum mechanics seemed to imply if taken seriously. The mathematics worked perfectly, too perfectly. Quantum mechanics predicted experimental results with astonishing precision, accurate to nearly one part in a trillion. Transistors, lasers, nuclear reactors, and modern computers all existed because the theory kept proving correct. But beneath its predictive success sat a fracture no one could properly explain. Particles behaved like possibilities. Before measurement, an electron did not possess one definite position or speed. Instead, it existed in superposition, meaning all possible states coexisted mathematically at once. A particle could occupy multiple paths simultaneously, carrying overlapping probabilities until observation occurred. Then came the strange part. Measurement appeared to force the possibilities into one actual outcome. Physicists called this wavefunction collapse. The wavefunction was the mathematical object containing every possible state of a quantum system, and collapse supposedly reduced it into a single observed reality. But what caused the collapse? No textbook answered clearly. The dominant Copenhagen interpretation, shaped largely by Niels Bohr during the 1920s, treated the question almost as forbidden territory. Students were taught to calculate outcomes, not ask what physically produced them. The equations delivered correct predictions, and for decades that was considered enough. Everett refused to stop there. As he studied the formal mathematics, he noticed something deeply unsettling. The equations themselves never required collapse at all. Nowhere inside Schrödinger's equation, the central equation governing quantum evolution, did collapse naturally appear. The mathematics only showed continuous development, smooth and unbroken. So Everett proposed something radical. The collapse never happens. When a measurement occurs, every possible outcome continues simultaneously, each in its own branching physical reality. One branch contains the observer who measured spin up, another contains the observer who measured spin down. Both branches persist, unaware of one another afterward. Reality splits cleanly, forever. His advisor, John Wheeler, immediately recognized the danger and brilliance of the idea. Wheeler admired Everett's mathematical consistency enough to personally travel to Copenhagen and present the work to Bohr himself, hoping for approval from the aging architect of quantum theory. The meeting failed almost instantly. Bohr rejected the framework outright. To him, Everett's interpretation seemed philosophically reckless, stripping away the special role of observation that Copenhagen preserved. Wheeler returned shaken and urged Everett to soften his claims before publication. He complied reluctantly. More than half the original thesis disappeared. Sections were rewritten, conclusions narrowed, language diluted. The final paper appeared in 1957 inside Reviews of Modern Physics, but Everett privately considered the published version deeply compromised. The damage lingered. Academic physics offered little encouragement afterward. Everett left the field within a year and moved into military defense analysis during the Cold War, helping design nuclear targeting systems and strategic models far removed from the foundations of reality that once consumed him. He rarely spoke publicly about many worlds again. In 1982, Hugh Everett died from a heart attack at 51 years old. Almost no one outside theoretical physics recognized his name then, but quietly, beneath the surface of modern science, younger physicists had already begun reopening the door he was told to close. A uranium atom sits silently for years, unchanged, until suddenly it decays. Another identical atom beside it does not. Quantum mechanics can predict the probability of decay with astonishing accuracy, yet it cannot tell you which individual atom will change first. At the smallest scales, nature behaves through probabilities instead of certainties. This is where Everett's interpretation becomes difficult to ignore. The many worlds interpretation begins with a simple refusal. It refuses to insert a mysterious collapse into equations that never required one mathematically. Instead, it accepts the equations exactly as written, then follows them to their full conclusion, regardless of how strange the destination becomes. Every quantum event contains multiple possible outcomes. A photon striking a detector may register on the left side or the right. An electron may reveal spin upward or downward. A radioactive particle may decay now or remain stable for another hour. Standard quantum mechanics says one outcome becomes real while the others disappear during measurement. But disappear how? Everett argued that nothing inside the mathematics removes the alternatives. The wave function, the mathematical description containing every possible state of a system, evolves smoothly and continuously at all times. It never deletes possibilities, it only expands. Under many worlds, all outcomes occur, not symbolically, physically. Reality branches into separate histories the moment quantum interaction forces different outcomes to diverge. One branch contains the observer who saw the particle decay, another contains the observer who saw stability continue. Both observers remember a single consistent outcome. Both believe they inhabit the only real world. Neither can detect the other. This separation is absolute. Once branching occurs, the resulting realities no longer interact. No signal crosses between them. No information leaks through. The split happens instantly at the quantum level and becomes permanent as the branches evolve independently afterward. The unsettling part is how ordinary this process would be. You would never feel a branch occur. No vibration passes through the room. No visible fracture appears in space. The branching would happen constantly inside microscopic interactions, shaping every neuron, molecule, and photon around you. Even simple choices become strange under this framework. Some branches contain versions of you who spoke different words earlier today. Others contain versions who stayed silent, arrived late, or never entered the room at all. Each version carries uninterrupted memories and complete confidence in their own continuity. From inside any branch, existence feels singular and stable. But beyond observation, alternatives persist. Critics often object that this multiplies realities extravagantly, producing unimaginable numbers of parallel histories every second. Everett accepted that implication completely. To him, the mathematics already implied this structure, whether physicists felt comfortable with it or not. And the central challenge never disappeared. If only one outcome truly survives after measurement, what physical mechanism destroys the others? Where inside the equations does elimination occur? Copenhagen interpretations often treat collapse as a special event outside ordinary quantum evolution, yet no universally accepted process has ever been identified experimentally. The missing mechanism still lingers quietly beneath modern physics. For nearly 7 decades, no consensus explanation has replaced it. A metal plate stands inside a dark laboratory. Cut into it are two narrow openings, each thinner than a human hair. Behind the plate sits a detection screen, waiting for impacts so small they cannot be seen directly by human eyes. The setup sounds almost childish, but it shattered physics. The double slit experiment began in the early 1800s with light, when Thomas Young demonstrated that light behaved like a wave. Water waves overlap and create interference, regions where crests strengthen or cancel one another. Light produced the same pattern after passing through two slits, proving it spread like a ripple rather than traveling as solid particles. Then quantum mechanics complicated everything. By the 1920s, physicists repeated the experiment using electrons, objects understood to be particles with measurable mass. The expectation seemed obvious. Fire electrons through two slits, and two impact bands should appear behind them. They did not. Instead, the detector produced an interference pattern identical to a wave passing through both slits simultaneously. Bright and dark bands emerged gradually across the screen, revealing overlapping probability peaks exactly as wave mathematics predicted. But electrons are not water. They arrive one at a time. Researchers slowed the experiment further. They fired individual electrons with minutes, sometimes hours, separating each emission. The result remained unchanged. Every isolated electron still contributed to the same interference structure, as though each particle somehow traveled through both openings simultaneously and interfered with itself before detection. This was not approximation, it was measured reality. Then physicists altered one detail. They placed a detector beside one slit to determine which path the electron actually used. Instantly, the interference pattern vanished. The electrons behaved like ordinary particles again, choosing one slit or the other without overlap. The act of measurement changed the outcome. Not forcefully, quietly. Simply obtaining path information destroyed the wave behavior. Remove the detector and the interference returned. Reintroduce observation and the wave vanished again. Thousands of experiments across decades confirmed the same pattern using electrons, photons, atoms, and increasingly massive structures. No consensus explanation followed. In 2019, researchers in Vienna demonstrated quantum interference using molecules containing roughly 2,000 atoms. These were not tiny subatomic particles anymore. They were large molecular systems approaching the boundary of visible matter under microscopes. Yet the interference survived. The dividing line between quantum behavior and everyday classical reality never appeared where physicists expected. Every improvement in experimental precision pushed the boundary further outward, as though nature refused to reveal where superposition truly ends. Many worlds treats this strangely naturally. Under Everett's framework, the electron does not choose a single path. One branch contains the particle passing left, another contains it passing right. Before environmental interactions separate those branches completely, their mathematical overlap produces the interference pattern measured experimentally. Nothing collapses, the branches simply diverge afterward. David Deutsch at Oxford pushed this interpretation further than most physicists dared publicly. Deutsch argued that quantum computation and interference only make sense if parallel branches physically exist. To him, the experiment already demonstrated multiple realities indirectly. The equations were not hiding metaphor beneath the surface, they were describing structure, and the structure kept matching observation with uncomfortable precision. Take a single grain of dust floating through sunlight. Left alone in perfect isolation, quantum mechanics says even that tiny speck could exist in multiple positions simultaneously, spread across overlapping possibilities like a blurred probability cloud. But isolation never truly happens. The dust grain collides constantly with surrounding air molecules, infrared radiation, stray photons, and microscopic thermal vibrations. Every interaction transfers information outward into the environment. The system becomes entangled, meaning its quantum state links inseparably with countless external particles around it. This process has a name: decoherence. It emerged gradually during the 1970s through work by physicists, including Dieter Zeh and Wojciech Zurek, who realized something crucial about why quantum superpositions vanish from ordinary experience without requiring mysterious collapse mechanisms. The environment itself destroys visibility between branches. When two possible quantum states interact with enough surrounding particles, they stop overlapping coherently. Mathematically, the branches become orthogonal, meaning separated into independent states, incapable of interfering with one another any longer. The distinction matters enormously. Under older interpretations, superpositions seem to disappear through observation alone, as though consciousness somehow forced reality into one definite outcome. Decoherence showed that conscious observers were unnecessary. Ordinary physical interaction already performed the separation automatically and relentlessly. The universe measures itself continuously. At room temperature, a human scale object decoheres almost instantly. Calculations place the timescale around 10 to the negative 43 seconds for certain macroscopic systems, shorter than any interval experimental physics can currently probe directly. Before a neuron fires or a heartbeat completes, decoherence has already isolated unimaginably vast numbers of microscopic possibilities from one another. This is why quantum behavior feels hidden, not because branching stops occurring, but because the branches lose the ability to interact afterward. Interference disappears once environmental entanglement spreads outward into trillions upon trillions of surrounding particles. The overlapping histories still exist mathematically and physically, yet they evolve separately from that point forward. Like sealed rooms, you remain trapped inside one consistent branch because every atom in your body has already decohered alongside the environment around it. Your memories, perceptions, and physical surroundings all stabilize together into one internally coherent history, while alternative branches continue elsewhere beyond interaction. Everett lacked this mechanism entirely. When he published his interpretation during the 1950s, critics attacked a central weakness. If branching truly happened, why did nobody observe bizarre overlapping realities directly? Everett could describe the mathematics elegantly, but he could not fully explain the apparent emergence of stable classical experience. Decoherence changed that. Suddenly, many worlds no longer depended on vague philosophical arguments about observers. It gained a concrete physical process describing how classical reality emerges naturally from quantum interactions without violating Schrödinger's equation at any stage. The shift inside physics happened slowly. Older generations remained skeptical, often loyal to Copenhagen traditions established decades earlier. But younger theorists, raised alongside quantum information theory and computational physics, found decoherence increasingly persuasive because it removed special rules and kept the mathematics continuous throughout. By 2021, surveys of physicists under 45 showed many worlds had become the single most popular interpretation of quantum mechanics among respondents. Not universally accepted, but no longer dismissible. Long before stars existed, before galaxies rotated through darkness, the universe was filled with dense plasma so hot that light itself could not travel freely. Photons scattered endlessly through charged particles, trapped inside an opaque cosmic fog. Then, expansion cooled everything. About 380,000 years after the Big Bang, temperatures finally dropped enough for electrons and atomic nuclei to combine into neutral atoms. Space suddenly became transparent. Light escaped for the first time and began traveling outward in every direction across the growing universe. That ancient radiation still surrounds us tonight. Physicists call it the cosmic microwave background, or CMB. It is the oldest electromagnetic signal humanity has ever detected, now stretched by cosmic expansion into faint microwave wavelengths, measuring about 2.7 degrees above absolute zero. Almost perfectly uniform, but not entirely. Tiny temperature variations ripple across the CMB at roughly 1 part in 100,000. These minute fluctuations became the seeds of everything familiar later on. Slightly denser regions gathered matter through gravity, eventually forming galaxies, stars, planets, oceans, and observers capable of mapping the sky billions of years afterward. In 2004, NASA's Wilkinson Microwave Anisotropy Probe, known as WMAP, revealed something unexpected buried inside that ancient pattern. A vast, cold region. It stretched across roughly 1.8 billion light years of sky, making it the largest anomalous structure ever identified in the observable universe. The temperature difference was subtle in ordinary terms, only about 70 microkelvin colder than surrounding regions, yet statistically, it stood far outside expected cosmological predictions. The anomaly became known simply as the cold spot. At first, astronomers searched for ordinary explanations. One leading proposal involved a supervoid, an enormous region containing far fewer galaxies than average. Light crossing such emptiness loses energy slightly through cosmic expansion, potentially creating colder regions in the microwave background through a process called the integrated Sachs-Wolf effect. In 2015, surveys confirmed a partial void existed in the same direction, but the numbers refused to align cleanly. The void was neither empty enough nor large enough to fully account for the observed temperature profile. Independent analyses kept reaching similar conclusions. Something remained unexplained within the structure itself. That uncertainty opened another possibility. Researchers at Durham University in England began comparing the cold spot's geometry against computer simulations of bubble universe collisions predicted by certain inflationary multiverse models. In those frameworks, our universe exists inside an expanding bubble of spacetime, surrounded by other bubbles forming elsewhere. Occasionally, bubbles collide. Such impacts should leave circular scars in the cosmic microwave background, regions where energy distributions become distorted during the earliest stages of cosmic expansion. The Durham simulations produced temperature profiles and spatial structures remarkably similar to the cold spot observations. The result entered peer-reviewed literature through monthly notices of the Royal Astronomical Society, one of the oldest astrophysics journals in existence. No consensus followed. Many cosmologists remain cautious, arguing statistical anomalies naturally appear in sufficiently large datasets. Others counter that the cold spot continues resisting conventional explanation despite 2 decades of increasingly precise measurements. But the unsettling possibility persists quietly beneath the debate. If the collision interpretation is correct, then another universe once touched ours physically, leaving a detectable imprint still visible across the oldest light in existence. Near midnight in 1979, Alan Guth covered pages with equations inside a small office at Stanford University, trying to resolve several cosmological problems that had resisted explanation for decades. By sunrise, he believed he had found a solution elegant enough to change the foundations of modern cosmology. The universe expanded violently at the beginning. That was Guth's insight. His proposal suggested that during the first fraction of a second after the Big Bang, specifically around 10 to the negative 36 seconds, space itself underwent exponential expansion driven by a quantum field later called the inflaton. A quantum field is an invisible physical field filling space, capable of storing energy and influencing how particles behave. The expansion was enormous. In less than an instant, the universe grew by at least a factor of 10 to the 26. Regions once smaller than atoms stretched beyond galactic scales. Space expanded faster than light itself, not because objects moved through space superluminally, but because space-time expanded underneath them. Several mysteries vanished immediately. The horizon problem disappeared because distant regions of the universe had once been close enough to equalize temperature before inflation separated them enormously. The flatness problem vanished because rapid expansion smoothed cosmic curvature almost perfectly flat, much like inflating a balloon makes any small patch appear straighter as it grows. Even tiny quantum fluctuations mattered suddenly. Microscopic irregularities stretched outward during inflation until they became the density variations later visible in the cosmic microwave background. Those variations eventually collapsed gravitationally into galaxies and stars. The structure of the modern universe emerged directly from quantum noise, amplified across cosmic scales. Physicists embraced inflation quickly because the evidence fit remarkably well, but the equations contained another consequence. Inflation did not end everywhere simultaneously. Quantum fluctuations inside the inflaton field caused some regions to stop inflating, while others continued expanding exponentially. Those still inflating regions grew faster than they decayed, meaning inflation became self-reproducing. New pockets of ordinary spacetime formed continuously inside an eternally inflating background. Each pocket became its own universe. Inside every bubble, inflation ended locally and released enormous energy, producing conditions similar to a Big Bang. But different bubbles could cool differently, evolve differently, or even settle into different physical constants, depending on the behavior of underlying quantum fields. Our universe became one bubble among countless others. The larger structure resembled cosmic foam, endlessly generating, expanding universes separated by inflating space, still stretching faster than light. Most bubbles remained permanently isolated because the intervening expansion outpaced any possible signal crossing between them. But collisions remained possible during formation. If two expanding bubbles touched before separating completely, the interaction should disturb the temperature distribution inside the surviving universes. The predicted signature would appear as circular anomalies embedded in the cosmic microwave background, colder or hotter regions carrying traces of the impact. The geometry matched certain unusual features already observed in the sky. That was never Guth's goal. Inflation originally existed to simplify cosmology, not multiply realities. Yet the mathematics repeatedly produced eternal inflation naturally once quantum behavior entered the equations. Guth himself later described the implication as philosophically uncomfortable because the theory seemed unable to avoid generating a multiverse once it began operating. The extra universes arrived uninvited, but they arrived mathematically unavoidable. In 1987, Steven Weinberg published a calculation that most physicists considered deeply uncomfortable, not because the mathematics failed, but because the logic behind it seemed almost unacceptable. Weinberg was not an outsider. He had already helped build the standard model of particle physics, the framework describing every known fundamental particle and force except gravity. In 1979, he received the Nobel Prize for work unifying electromagnetism with the weak nuclear force. His reputation inside physics was immense, and yet the problem confronting him seemed almost absurd. The cosmological constant, first introduced reluctantly by Einstein in 1917, described the energy contained within empty space itself. Empty space was not truly empty. It possessed a faint vacuum energy capable of pushing the universe outward against gravity. Einstein later abandoned the constant. Then observations resurrected it decades afterward. But before those observations arrived, no one understood why the constant appeared so tiny. Quantum field theory predicted vacuum energy values catastrophically larger than anything compatible with reality. Depending on the calculation, the theoretical prediction overshot the observed value by roughly 120 orders of magnitude, the worst mismatch between theory and experiment in modern science. Weinberg approached the problem differently. Instead of asking why the constant possessed one exact value, he considered the possibility that many universes existed, each carrying different physical constants distributed across a vast cosmic landscape. Most universes would expand too violently or collapse too rapidly for galaxies to form. Observers would never appear there. Only universes with narrowly balanced constants could produce stars, chemistry, planets, and eventually physicists wondering why the numbers looked so improbable. This reasoning became known as the anthropic principle, meaning observations are filtered by the conditions required for observers to exist at all. Weinberg calculated the upper limit. If the cosmological constant exceeded a certain threshold, matter would disperse before galaxies formed. The universe would become thin, cold, and structurally empty long before life emerged. Using multiverse reasoning, Weinberg predicted the constant should lie near the largest value still compatible with galaxy formation. He published the estimate. 11 years later, in 1998, two independent supernova teams measured the accelerating expansion of the universe directly through distant exploding stars. Their data revealed a small but non-zero cosmological constant, astonishingly close to Weinberg's predicted range. The calculation worked. Not philosophically, quantitatively. That distinction matters enormously in physics. Theories gain credibility when they produce measurable predictions before observations occur independently afterward. Weinberg's argument did exactly that, using assumptions tied directly to multiverse reasoning. The measured value itself remains extraordinary. In natural units used by theoretical physicists, the cosmological constant equals roughly 10 to the negative 122. If the value increased by even 10 to the negative 60 relative to its present magnitude, gravitational structure could never stabilize into galaxies. Stars would not form. Neither would you. Critics argue this does not prove multiple universes exist. They are correct. But the prediction remains difficult to dismiss because the multiverse framework did not merely accommodate the observed value afterward. It anticipated the narrow, habitable range beforehand. Few multiverse arguments reach that level of precision. Fewer still survived observation intact. Two equations dominate modern physics with almost terrifying success. Quantum mechanics governs the microscopic world of particles and probabilities. General relativity governs gravity, spacetime, stars, and galaxies across cosmic scales. Separately, they work beautifully. Together, they fail. Inside black holes or during the first instant after the Big Bang, both theories become necessary simultaneously. But when physicists combine them mathematically, infinities erupt through the calculations. The equations stop producing meaningful predictions and collapse into contradictions no experiment can interpret cleanly. For decades, this became physics' deepest unfinished problem. String theory emerged as one possible solution during the late 1960s and early 1970s. Instead of treating particles as infinitely small points, the theory proposed something stranger. Every particle was actually a tiny vibrating strand of energy, unimaginably small and one-dimensional. Different vibrations produced different particles. An electron represented one vibrational pattern, a quark represented another. Even gravity emerged naturally through a specific vibration associated with a hypothetical particle called the graviton. Suddenly, forces and matter looked less like separate ingredients and more like harmonics inside one underlying framework. The mathematics became astonishingly elegant, but it demanded extra dimensions. Ordinary experience reveals three spatial dimensions and one dimension of time. String theory required 10 dimensions total, or 11 in more advanced versions called M theory. The additional dimensions were assumed to exist in tightly curled geometric structures too small for direct detection. And there the trouble began. Those hidden dimensions could fold into enormous numbers of stable configurations. Each possible geometry altered the resulting physics inside the universe that emerged from it. Particle masses changed. Force strengths changed. Even the number of stable particles could vary depending on how the dimensions compactified, meaning curled into microscopic shapes. Each configuration described a different universe. At first, theorists hoped only one mathematically stable arrangement would survive deeper analysis. They searched for years, trying to eliminate the excess solutions and recover one unique cosmos matching ours precisely. The solutions multiplied instead. By the early 2000s, estimates suggested roughly 10 to the 500 possible stable compactifications existed inside string theory. That number is so vast it exceeds comprehension. It represents more possible universes than atoms in the observable cosmos by an unimaginable margin. Physicists named this collection the landscape. Leonard Susskind, one of string theory's founders, gradually concluded the landscape was not a temporary flaw waiting for removal. It was an unavoidable consequence of the mathematics itself. Combined with eternal inflation, the implication became difficult to escape. Each inflating bubble universe could settle into a different compactification, producing entirely different laws of physics across the multiverse. Not metaphorically different, fundamentally different. Some universes might contain stronger gravity, unstable atoms, or no chemistry at all. Others could possess radically altered particle families or dimensions large enough to experience directly. Our universe became one habitable location among staggering variation. This created deep discomfort within theoretical physics. A theory explaining everything was suddenly predicting almost anything. If 10 to the 500 universes exist, each with different constants, then string theory struggles to explain uniquely why our specific laws appear here rather than elsewhere. The framework remained mathematically powerful, but its predictive certainty dissolved into cosmic plurality. Beneath farmland near Geneva, buried about 100 meters underground, protons circle through darkness inside a tunnel so large that passenger trains could fit comfortably within sections of it. Superconducting magnets, cooled colder than deep space, bend the particles around a ring stretching 27 kilometers beneath the French-Swiss border. This is the Large Hadron Collider, the most powerful particle accelerator ever constructed. When operations began in 2008 at CERN, the European Organization for Nuclear Research, expectations inside physics were enormous. The machine would recreate energies not seen naturally since fractions of a second after the Big Bang, allowing physicists to probe deeper into matter than any experiment before it. One target stood above the rest: the Higgs boson. The Higgs field permeates all space, and particles interacting with it acquire mass through that interaction. Detecting the Higgs would confirm the final missing piece of the Standard Model. In 2012, CERN announced its discovery. The result matched predictions with remarkable precision, and the Nobel Prize followed 1 year later. But another search mattered quietly in the background: supersymmetry. Supersymmetry proposed that every known particle possessed a heavier partner particle called a sparticle. Electrons would have selectrons, quarks would have squarks, photons would have photinos. The names sounded almost playful, yet the implications were profound. These particles solved multiple theoretical problems simultaneously. Supersymmetry stabilized certain quantum calculations that otherwise exploded into infinities. It offered candidates for dark matter. Most importantly, for string theory, supersymmetry made the mathematics internally consistent at extreme energies. Finding sparticles would not prove the multiverse directly, but it would strengthen the frameworks supporting string theory, eternal inflation, and the landscape of possible universes discussed earlier. Many physicists expected at least some supersymmetric particles to appear once the collider reached sufficient energy levels. Years passed. Nothing appeared. The collider kept smashing protons together at higher and higher energies, generating showers of exotic particles lasting tiny fractions of a second before decaying. Detectors recorded petabytes of data. Analysts searched relentlessly for signatures beyond the Standard Model. The sparticles never arrived. Physicists began calling the absence the desert, an unexpectedly empty region of physics beyond the Higgs scale, where many theories predicted rich new particle families. Instead, nature remained strangely quiet. That silence changed the conversation. For critics of the multiverse and string theory, the missing particles became evidence that entire theoretical programs may have wandered too far from experimental reality. Elegant mathematics alone no longer seemed sufficient if the predicted structures refused to materialize. But supporters interpreted the result differently. Inside the landscape picture, countless universes exist with different physical constants and energy scales. Our universe may simply inhabit a region where supersymmetric particles lie beyond current experimental reach, or where low-energy supersymmetry never emerged visibly at all. The same data supported opposing conclusions, and that tension still defines modern theoretical physics. The collider did not fail. It answered exactly what experiments are designed to answer. The universe either contains accessible supersymmetric particles, or it does not within the energies explored so far. Nature responded with silence, and sometimes silence forces deeper reconsideration than discovery itself ever could. The reckoning remains unfinished. Close a laboratory door and imagine nobody outside can see inside. Within that sealed room, a scientist measures a quantum particle and records a definite result. The particle spins upward. A detector confirms it. Notes are written. From inside the room, reality appears settled and complete. But outside the door, another observer waits. This was the strange scenario proposed by physicist Eugene Wigner in 1961. Wigner already understood the problems surrounding quantum measurement, yet he realized something deeper remained unresolved once observers themselves became part of the experiment. From the friend's perspective, the measurement ended. From Wigner's perspective, it did not. Quantum mechanics allows outside observers to describe unmeasured systems as superpositions, combinations of multiple possible states existing simultaneously. Since Wigner has not interacted with the sealed laboratory directly, the entire room should remain mathematically suspended in superposition from his viewpoint. Not only the particle, everything inside, the detector, the notebook, the scientist observing the result, all remain part of one unresolved quantum state, according to the external description. Inside the room, the scientist insists the particle spun upward. Outside the room, Wigner's equations still describe both upward and downward outcomes existing together. Both descriptions follow quantum mechanics correctly. That is the problem. Under traditional interpretations, only one objective reality should exist at a time. Yet the theory itself permits incompatible accounts simultaneously depending on the observer's relationship to the measurement. The contradiction sat uneasily inside physics for decades, treated mostly as philosophical abstraction rather than experimental science. Then technology advanced enough to test the logic directly. In 2019, researchers at Heriot-Watt University in Edinburgh created a laboratory version of the Wigner's friend scenario using entangled photons. Entanglement means two particles share linked quantum states, such that measuring one immediately constrains the other, regardless of separation. The experiment simulated multiple observers performing incompatible measurements on the same quantum system. One observer recorded a definite outcome internally, while another observer described the larger combined system externally through superposition. The results revealed something deeply unsettling. The observers could not reconcile their accounts into one shared objective description without violating the mathematical predictions of quantum mechanics itself. Reality depended on perspective. The findings appeared in Nature Physics, among the most respected journals in the field. Yet, outside quantum foundations, the paper passed quietly through public awareness despite touching one of the oldest unresolved fractures in modern science. What exactly becomes real, and for whom? The Copenhagen interpretation struggles here because it assumes measurements produce single outcomes universally. But Wigner's setup forces contradictory observational realities into coexistence. One observer sees resolution. Another still sees superposition. Many worlds absorbs the contradiction naturally. Wigner and his friend occupy different branches after the measurement interaction occurs. Each branch contains internally consistent observers experiencing definite outcomes within their own reality. Neither observer accesses the other branch afterward because decoherence isolates the histories completely. Both descriptions remain valid locally. Neither possesses universal priority. The experiment did not prove parallel universes definitively, but it demonstrated something equally uncomfortable. Quantum mechanics may not describe one shared observer, independent reality beneath appearances. Instead, the structure of reality itself may depend partly on the observer embedded within it, and the equations continue, permitting that possibility without resistance. In 1935, Albert Einstein published a paper he believed would expose a fatal weakness inside quantum mechanics. By then, he had already reshaped physics through relativity, altering humanity's understanding of space, time, gravity, and motion itself. But quantum theory disturbed him. Its equations predicted probabilities instead of certainties, and its strange behavior seemed incompatible with the orderly reality Einstein believed must exist beneath appearances. He spent the last decades of his life searching for evidence that the theory was incomplete. The challenge became known as the EPR paradox, named after Einstein, Boris Podolsky, and Nathan Rosen. The setup involved two particles interacting briefly before separating across large distances. Quantum mechanics predicted the particles would remain entangled afterward, meaning their properties stayed linked through one shared quantum state even while physically distant. Measure one particle, and the other responds instantly. If one particle reveals spin upward, the distant partner immediately assumes the complementary state required by the shared system. The effect appears regardless of whether the particles are separated by meters or light years. Einstein rejected this completely. Nothing, according to relativity, should influence another object faster than light. He mocked the phenomenon as spooky action at a distance and argued hidden variables must secretly determine outcomes beforehand. Quantum mechanics only looked incomplete because deeper information remained undiscovered. For decades, the argument stayed philosophical. Then, in 1964, physicist John Bell changed everything. Bell derived a mathematical inequality capable of distinguishing hidden variable theories from genuine quantum entanglement. If Einstein was correct, the inequality would always hold statistically. If quantum mechanics was correct, it would fail. Experiments followed gradually through the following decades. Most importantly, Alain Aspect and his team in France performed increasingly precise entanglement tests during the early 1980s using polarized photons separated during flight. The measurements violated Bell's inequality repeatedly and decisively. Einstein's hidden variables failed. Later experiments strengthened the conclusion using larger separations, faster detectors, and stricter controls. In 2022, Aspect received the Nobel Prize in Physics for helping confirm entanglement experimentally. The implications remain extraordinary. Entangled particles do not behave like separate independent objects. They behave like components of one extended quantum system spread across space. Measuring one instantly constrains the possibilities available to the other even though no usable signal passes between them. This does not allow faster than light communication. Observers only discover the correlation afterward by comparing measurements through ordinary signals limited by relativity. But locality itself, the assumption that only nearby things directly affect each other, no longer appears fundamental at quantum scales. Many worlds interprets this differently. Under Everett's framework, entangled particles branch together during measurement. One observer enters the branch where the first particle appears upward and the second downward. Another branch contains the reverse arrangement. The correlation emerges naturally because both particles remain parts of the same branching structure. The particles were never fully separate to begin with. A glass falls from a table and shatters across the floor. The fragments scatter outward. Heat disperses into the room, and the process feels irreversible in a way so familiar that we rarely examine it closely. But the equations do not care. At the deepest level known to physics, the fundamental laws governing particles and forces remain almost entirely time symmetric. Run the equations of quantum mechanics backward, and they still function. Reverse general relativity, mathematically, and space-time obeys the same rules. Nothing inside the core equations clearly distinguishes past from future. Yet experience does. You remember yesterday, but not tomorrow. Stars burn fuel instead of gathering ash back into themselves. Ice melts into water. Smoke spreads through air. Disorder increases naturally. This directional flow comes from entropy. Entropy measures the number of microscopic arrangements corresponding to a larger physical state. Ordered systems possess fewer possible arrangements. Disordered systems possess vastly more. The second law of thermodynamics states that entropy tends to increase statistically because random motion overwhelmingly favors disorder over order. But tens matters enormously. The law is probabilistic, not absolute. In principle, particles inside a room could spontaneously organize themselves into perfect structure again. The probability is simply so tiny that it effectively never occurs within the lifetime of the universe, which raises a deeper problem. If entropy naturally increases, why did the universe begin in such an extraordinarily ordered condition to begin with? The Big Bang was not chaotic in the thermodynamic sense. It possessed remarkably low entropy despite containing immense energy and density. Roger Penrose attempted to quantify this improbability mathematically. His estimate for a universe beginning in a state as ordered as ours was approximately 1 chance in 10 raised to the power of 10 raised to the power of 123. The number is so extreme that ordinary language fails completely beside it. Writing the zeros alone would require vastly more space than exists inside the observable universe. Something selected those initial conditions. Under a single universe framework, that selection appears almost impossibly special. Either the cosmos began in an unexplained state of precision for no deeper reason, or some principle outside known physics constrained the beginning artificially. But another possibility emerged. Physicists Sean Carroll and Jennifer Chen proposed that the multiverse itself may exist in an overall high entropy state. Within that broader background, low entropy regions occasionally fluctuate into existence locally. Our universe would represent one such fluctuation, a temporary pocket where entropy increases away from an unusually ordered starting point. Time's arrow becomes local instead of universal. Inside our bubble, entropy increases toward what we call the future because we originated near a low entropy boundary condition. Observers naturally experience the direction of increasing entropy as forward because memory, formation, biological processes, and causality all depend on irreversible thermodynamic flow. But elsewhere, the orientation could reverse. In another bubble universe, entropy might increase relative to what we would label the past. Observers there would still experience their direction as normal because consciousness follows local thermodynamic gradients automatically. The distinction between past and future may not belong to reality itself. It may belong only to where inside reality you happen to exist. Roger Penrose spent decades operating near the limits of mathematical physics. Moving through ideas, most researchers approached cautiously, if at all. Long before discussions about multiverses entered mainstream science, Penrose had already helped prove that black holes and singularities were unavoidable consequences of general relativity alongside Stephen Hawking during the 1960s. His reputation carried enormous weight. By 2010, Penrose proposed a cosmological model stranger than eternal inflation, yet built from rigorous mathematics rather than speculation. He called it conformal cyclic cosmology, usually shortened to CCC. The idea rejected parallel universes existing simultaneously. Instead, universes arrived sequentially. Under Penrose's framework, the far future of one universe eventually becomes mathematically equivalent to the Big Bang of the next. After unimaginable spans of time, stars burn out, galaxies disperse, and black holes slowly evaporate through Hawking radiation, a quantum process causing black holes to lose energy gradually across enormous timescales. The waiting period is staggering. Large black holes may require roughly 10 raised to the power of 100 years to disappear completely. Yet once all mass decays and only radiation remains, Penrose argued, the universe loses meaningful scales of distance and time. Without massive particles, the extremely expanded future begins resembling the compressed conditions before a Big Bang mathematically. One cosmic cycle flows into another. Our universe would not be unique or first. It would represent one phase in an endless succession of aeons, each born from the thermodynamic exhaustion of the previous cosmos. But Penrose did something important. He made a prediction. If supermassive black holes existed in the universe before ours, their violent interactions and final evaporation events should leave subtle traces inside the cosmic microwave background. Specifically, Penrose predicted faint circular regions with unusually low temperature variance embedded within the CMB sky. Rings. In 2010, Penrose and Armenian physicist Vahe Gurzadian published a paper claiming those rings had already been identified within microwave background data gathered by the Wilkinson Microwave Anisotropy Probe. The response came almost immediately. Within weeks, 3 independent research groups reanalyzed the same datasets and concluded the circular patterns were statistically consistent with ordinary, random fluctuations expected inside noisy, cosmological measurements. According to the rebuttals, the rings were not extraordinary structures at all. They were artifacts. Penrose disagreed sharply. He argued the opposing analyses misunderstood the statistical framework underlying his prediction and improperly characterized the temperature distributions involved. The disagreement never fully resolved. Papers and counterarguments continued circulating through the literature afterward without reaching broad consensus. But something about the reaction stood out. The speed mattered. When one of the world's most respected mathematical physicists published possible evidence for pre-Big Bang universes, the response from the cosmology community mobilized with unusual urgency. That does not prove Penrose correct. Scientific scrutiny is necessary, especially for extraordinary claims. Yet the intensity revealed discomfort. Conformal cyclic cosmology threatens more than technical assumptions. It challenges the idea that the Big Bang marked an absolute beginning. It replaces a singular origin with endless recurrence, turning cosmic history into something cyclic and potentially eternal. The rings remain unresolved. Current microwave background data lacks sufficient precision to settle the question definitively. For now, the patterns remain suspended between statistical accident and possible evidence that another universe existed before this one began. Galaxies rotate too quickly. That realization arrived gradually during the 20th century as astronomers began measuring how fast stars moved around galactic centers. According to gravity, stars near the outer edges should orbit more slowly because most visible matter sits toward the middle. But they did not slow down. The outer stars moved so rapidly that galaxies should have torn themselves apart long ago unless something unseen supplied additional gravity holding them together. The same discrepancy appeared inside galactic clusters, where enormous collections of galaxies bent surrounding light far more strongly than visible matter alone could explain. Something invisible dominates the cosmos. Physicists named it dark matter. Current measurements suggest roughly 27% of the universe consists of this unknown substance, outweighing ordinary atoms by approximately 5 to 1. Without dark matter, galaxies like the Milky Way may never have formed at all because early matter distributions lacked enough gravitational pull to condense efficiently after the Big Bang. Yet, dark matter remains strangely absent from laboratories. For decades, underground detectors buried beneath mountains searched for faint particle interactions shielded from cosmic radiation. Particle accelerators hunted for missing energy signatures. Telescopes mapped the sky with increasing precision. Candidate particles emerged repeatedly, including WIMPs, meaning weakly interacting massive particles, along with axions and sterile neutrinos. None appeared. Every major predicted dark matter particle has remained experimentally invisible within expected ranges so far. The silence forced some physicists toward more radical possibilities. One possibility involves extra dimensions. In certain versions of string theory, our universe exists on a brane, meaning a membrane embedded within a higher dimensional structure called the bulk. Ordinary particles and forces remain trapped on our brane, unable to move freely into surrounding dimensions. Electromagnetism stays confined. So do the strong and weak nuclear forces. But gravity behaves differently in some models. Because gravity arises from spacetime geometry itself, it may extend through the bulk instead of remaining locked to a single brane. Gravitational influence could leak between neighboring universes existing beside ours in higher dimensional space. That changes everything. Matter inside another brane would remain completely invisible through light or ordinary particle interactions. You could not touch it, see it, or detect it electromagnetically. Yet its gravity would still affect our universe across the dimensional separation, which resembles dark matter exactly. The stars orbit too quickly because hidden matter exists nearby, not inside our visible universe, but beside it within the bulk. Entire galaxies could occupy neighboring branes pressed unimaginably close to ours while remaining permanently inaccessible except through gravitational effects. A shadow universe. The dimensional separation in some models may be smaller than an atomic nucleus, despite containing entire cosmic structures extending across millions of light years internally. Distance behaves differently once higher dimensions enter the equations. The Large Hadron Collider searched partly for evidence supporting these possibilities. Physicists examined collisions for signs of particles vanishing suddenly into extra dimensions, carrying energy away from our brane into the bulk itself. Nothing definitive appeared, but the explored energies remain limited compared to scales where these effects may emerge strongly. The absence constrains the models without eliminating them completely. For now, dark matter remains unresolved, suspended between unknown particles and the possibility that another universe may already be gravitationally touching our own from just beyond ordinary space. Inside a refrigerated chamber colder than interstellar space, delicate electrical circuits hover near absolute zero, while microwave pulses flicker across superconducting loops smaller than a fingernail. The machine appears almost motionless from outside. But inside, something profoundly unfamiliar may be happening. In October 2019, Google announced that its Sycamore quantum processor completed a specialized calculation in approximately 200 seconds. According to Google's estimate, The same task would require around 10,000 years on the world's fastest classical supercomputer. IBM challenged that number afterward. Its engineers argued a highly optimized classical approach could potentially finish the calculation within days rather than millennia, but the broader point survived the dispute untouched. Quantum processors were solving certain problems through methods fundamentally different from ordinary computation. Classical computers process possibilities sequentially. Even enormously powerful supercomputers still evaluate operations step by step, moving through calculations one state after another at extraordinary speeds. A quantum computer behaves differently because it uses qubits, meaning quantum bits capable of existing in superposition. A qubit can represent multiple states simultaneously. As additional qubits become entangled together, the number of possible combined states expands exponentially. 50 entangled qubits can encode more possible configurations than there are stars in the observable universe. The machine does not examine each configuration individually in sequence. It evolves through all of them together. This is where physicist David Deutsch enters the story. Deutsch, working at Oxford during the 1980s, became one of quantum computing's founders, while also emerging as one of the strongest advocates for many worlds. His argument was blunt and deeply controversial. If quantum computers genuinely process vast numbers of possibilities simultaneously, where exactly are those computations physically occurring? Not metaphorically, physically. A quantum algorithm works because probability amplitudes, mathematical quantities describing possible outcomes, interfere with one another. Incorrect computational paths cancel themselves through destructive interference, while correct paths reinforce through constructive interference. The final measurement reveals an answer shaped by interactions among enormous numbers of simultaneous possibilities. Deutsch insists those possibilities must correspond to something real. Otherwise, the calculations emerge from nowhere. Under many worlds, the explanation becomes straightforward. Different branches of the universal wavefunction perform different parts of the computation independently before interference combines the results mathematically. Parallel branches are not philosophical decoration. They become part of the machine's operating substrate. The other universes help perform the calculation. Deutsch has defended this interpretation literally for more than 40 years. Another detail strengthens the connection. Quantum computation remains extremely fragile because environmental interactions destroy superpositions rapidly through decoherence, the same process discussed earlier that separates branching realities from one another. To prevent collapse, engineers use quantum error correction. Quantum error correction distributes information across entangled states. So delicate quantum coherence survives noise and interference from the environment. The mathematics describing this protection mirrors the mathematics governing decoherence itself with striking precision. The resemblance is not superficial. Quantum computers function only because nature permits coherent superpositions to persist temporarily before decoherence isolates outcomes into classical reality. Every successful quantum computation depends on managing that boundary carefully enough for interference among possibilities to remain physically meaningful. And the machines keep working. Whether the parallel branches are literally real remains disputed fiercely across physics. But each functioning quantum processor forces the same uncomfortable observation back into view. Nature behaves as though multiple possibilities coexist simultaneously long enough to influence measurable outcomes before ordinary reality settles into place again. Life on Earth evolves through selection. Small variations appear between generations, and environments gradually preserve the traits most successful at surviving long enough to reproduce. Over immense spans of time, simple replication produces astonishing complexity without any guiding intention behind it. In 1992, physicist Lee Smolin asked a strange question: what if universes evolve the same way? Smolin worked at the Perimeter Institute in Canada and approached the multiverse differently from inflationary cosmology or quantum branching. His proposal began not with microscopic particles, but with black holes, the collapsed remnants of massive stars where gravity compresses matter beyond ordinary limits. Inside general relativity, black holes terminate in singularities. A singularity is a region where spacetime curvature becomes mathematically infinite and current physics stops functioning properly. But many physicists suspect true infinities never exist physically. Quantum gravity, whatever final form it takes, may soften the collapse before infinite density occurs. Smolin proposed a possibility. Instead of ending completely, the collapsing core inside a black hole rebounds under quantum gravitational effects and creates a new expanding region of spacetime on the other side. A new universe forms, disconnected permanently from the parent universe that produced it. Every black hole becomes a cosmic seed. Our universe contains extraordinary numbers of them. Hundreds of billions of galaxies spread across observable space, each containing hundreds of billions of stars, have generated immense populations of black holes during cosmic history. If each one produces another universe, then universes reproduce constantly. But Smolin added one more idea. The offspring universes inherit the physical constants of the parent universe with small, random variations, similar to genetic mutation in biology. Quantities such as particle masses, force strengths, and nuclear interactions shift slightly between generations. Now, natural selection enters cosmology. Universes producing many black holes create many offspring universes. Universes poor at black hole formation leave fewer descendants. Across enormous chains of cosmic reproduction, the multiverse gradually becomes dominated by universes optimized for generating black holes efficiently. That includes ours. Smolin's framework makes a measurable prediction. If cosmological natural selection is correct, our universe's constants should already sit near values maximizing stellar black hole production. Small changes to those constants should reduce black hole formation rather than improve it. This made the theory scientifically vulnerable. Predictions can fail. Astrophysicists Fred Adams and Greg Laughlin explored the question computationally at the University of Michigan by modeling how altered physical constants affected star formation and collapse. Their results suggested our universe indeed lies surprisingly close to optimal conditions for producing stellar black holes. Not perfectly optimized, but remarkably efficient. This does not prove Smolin correct. Many uncertainties remain about black hole interiors and quantum gravity, yet the framework generated a successful prediction from multiverse reasoning, something critics often claim such theories cannot do at all. The deeper implication lingers quietly beneath the mathematics. Our universe may not be random. The stars, the heavy elements, the stability of matter, even the conditions allowing biological life could exist because countless prior universes failed to reproduce effectively. We may inhabit a cosmos shaped through an evolutionary process stretching backward across generations, so ancient that ordinary concepts of beginning lose meaning entirely. Far out in the future of an eternal universe, long after stars have died and galaxies drift beyond visibility, physics predicts something deeply unsettling may still occasionally happen. Random order appears from chaos. The idea traces back to Ludwig Boltzmann, the 19th century physicist who helped develop statistical thermodynamics, the framework explaining entropy through probability rather than certainty. Boltzmann understood that if a system exists long enough, random fluctuations inevitably produce temporary decreases in entropy purely by chance. Usually the fluctuations are tiny. A few particles align briefly. A pocket of gas becomes slightly more ordered than expected, but given enough time and enough space, larger fluctuations also become possible. Probability never reaches zero. It merely becomes unimaginably small, and eventually, small probabilities occur. A sufficiently large fluctuation could theoretically assemble something astonishingly complex from thermal randomness alone, not an entire planet, not even an entire civilization. The simplest fluctuation capable of producing conscious experience would be vastly smaller, just a brain. A fully formed, self aware brain could emerge briefly from chaotic particles with artificial memories already intact, memories of childhood, history, identity, and a life that never actually happened. The brain would experience consciousness for an instant before dissolving back into disorder almost immediately afterward. This hypothetical observer is called a Boltzmann brain. At first, the concept sounds absurd enough to ignore, but the mathematics becomes difficult inside eternal, multiverse models. In an infinitely old or infinitely large cosmos, random fluctuations eventually outnumber ordinary biological evolution simply because there is limitless time available for rare events to occur repeatedly. That creates a statistical crisis. If Boltzmann brains vastly outnumber evolved observers like us, then any randomly selected conscious being should most likely be one of them, which means the statistically favored explanation for your current awareness would not be that you evolved on Earth through billions of years of cosmic history. It would be that you fluctuated into existence moments ago with false memories already embedded artificially inside your mind. Nothing you remember would necessarily be real. Most physicists reject that conclusion instinctively because it collapses ordinary reasoning itself. Science depends on trusting observations, memories, and continuity across time. A universe dominated by Boltzmann brains undermines all three simultaneously, but the logic remains internally consistent. That is what makes the problem dangerous. The solution proposed most often involves the universe's extremely low entropy beginning discussed earlier. If cosmological conditions strongly favor stable evolutionary histories over isolated random fluctuations, then ordinary observers may still vastly outnumber Boltzmann brains, despite eternal cosmic timescales. But this only works under certain multiverse structures. Some models generate too many random observers and therefore become self-defeating statistically. A viable cosmology must produce a universe where coherent histories dominate over accidental conscious fluctuations. Otherwise, the theory predicts that almost everyone observing reality should possess fictional memories and no genuine past. The Boltzmann brain problem does not disprove the multiverse. Instead, it acts like a filter. Any multiverse framework leading overwhelmingly toward random isolated consciousness probably contains something fundamentally incomplete. The equations must describe a cosmos where observers like us emerge naturally through stable cosmic evolution rather than through momentary accidents inside eternal chaos. In the final weeks of his life, Stephen Hawking was still working. His body had weakened for decades under amyotrophic lateral sclerosis, the neurodegenerative disease that gradually removed nearly all voluntary muscle control. Yet, his mind continued moving through cosmology, black holes, and the structure of the early universe with the same restless intensity that had defined his career since the 1960s. In March 2018, Hawking approved the last revisions of a paper developed over 2 years alongside Belgian physicist Thomas Hertog at KU Leuven. 10 days later, he died. The paper carried a deceptively calm title, A Smooth Exit from Eternal Inflation. Beneath that title sat one of the deepest unresolved problems in multiverse physics: infinity. Standard eternal inflation produces an endlessly branching cosmic structure where bubble universes form continuously forever. Every physically possible arrangement eventually occurs somewhere. Every set of constants appears somewhere. Every history unfolds somewhere. At first, this seems powerful, but a theory predicting everything predicts nothing specifically. If all outcomes occur infinitely often, extracting meaningful probabilities becomes nearly impossible. The framework loses explanatory sharpness because no observation uniquely favors one prediction over another. Hawking considered this unacceptable. His final work attempted to constrain the multiverse mathematically rather than abandon it entirely. The solution drew from the no-boundary proposal, a quantum cosmology model Hawking originally developed with James Hartle during the 1980s. The no-boundary proposal describes the early universe without requiring a sharp temporal beginning. Near the Big Bang, space-time behaves quantum mechanically, blurring ordinary distinctions between space and time themselves. Instead of emerging from an infinitely precise singularity, the universe transitions smoothly from quantum geometry into classical expansion. Hawking and Hertog extended this idea into eternal inflation. Their conclusion was subtle but important. The multiverse may not branch infinitely in all possible directions. Instead, the structure of bubble universes could be constrained by the geometry of the initial quantum state underlying cosmic inflation. Not every universe becomes allowed. Variation remains finite and structured. That changes the scientific status of the idea dramatically, because finite models generate measurable predictions. A constrained multiverse can potentially be tested against observation and ruled out if reality disagrees. Hawking's final paper pointed toward gravitational waves. Gravitational waves are ripples in spacetime itself, produced by accelerating mass and violent cosmic processes. Inflation during the earliest moments after the Big Bang should have generated primordial gravitational waves, carrying information about the universe's initial quantum structure. Different inflationary models predict different wave patterns. A bounded multiverse leaves signatures distinct from unconstrained eternal inflation. Hawking and Hertog argued future detectors may eventually distinguish between them observationally. One instrument matters especially here: the Laser Interferometer Space Antenna, usually called LISA, is a planned European Space Agency mission expected during the 2030s. 3 spacecraft separated by millions of kilometers will measure tiny distortions in spacetime with extraordinary sensitivity, potentially detecting primordial gravitational signals from the infant universe itself. Hawking's final scientific act was not philosophical, it was methodological. He spent his last years trying to transform the multiverse from an unfalsifiable abstraction into something science could genuinely test against reality. The paper appeared in the Journal of High Energy Physics in May 2018, 1 month after his death. Even at the end, he was still trying to bring the infinite back within reach of observation. Scientific revolutions rarely happen through sudden, unanimous agreement. More often, they unfold through hesitation, Reversals, partial concessions, and long periods where even the people closest to the mathematics cannot decide what they believe. The multiverse followed that pattern exactly. John Wheeler understood this better than most. During the 1950s, he supervised Hugh Everett's doctoral work at Princeton and initially recognized the brilliance inside Everett's attempt to remove wave function collapse from quantum mechanics entirely. But Wheeler admired Niels Bohr deeply. After Bohr rejected Everett's interpretation in Copenhagen, Wheeler distanced himself gradually from the theory he had once defended enthusiastically. For years, he treated many worlds cautiously, almost reluctantly. Yet during the 1970s, as decoherence and quantum foundations developed further, Wheeler began acknowledging quietly that Everett's framework solved problems. Other interpretations avoided confronting directly. Then he hesitated again. Late in life, Wheeler pulled back over concerns about experimental testability. The mathematics impressed him. The philosophy unsettled him. He never fully settled the conflict internally. Martin Rees reached a different conclusion. Rees, the astronomer royal of the United Kingdom and one of the world's most respected cosmologists, has stated publicly that he would bet his life on the existence of the multiverse. Not because direct evidence already confirms it completely, but because several independent areas of physics seem to converge naturally toward it. Yet even Rees admits the limitations clearly. Belief is not proof. Elsewhere, the debate became even sharper. Paul Steinhardt helped develop inflationary cosmology alongside Alan Guth during the early 1980s. Inflation solved major problems elegantly and became central to modern cosmology within years. But Steinhardt eventually grew alarmed by eternal inflation. The framework became so flexible that almost any observation could potentially fit somewhere inside its infinite landscape. To Steinhardt, this threatened the core principle separating science from metaphysics. A theory explaining every outcome risks losing predictive power entirely. So he became one of inflation's strongest critics. Not because he misunderstood the mathematics, but because he understood it deeply enough to worry where it led philosophically. Andre Linde traveled the opposite path. Linde independently developed eternal inflation and became perhaps its most vocal defender. He embraced the multiverse implications directly rather than resisting them. Yet even Linde has acknowledged serious unresolved issues, especially the Boltzmann brain problem discussed earlier. No position remains fully comfortable. That is what makes the conversation unusually revealing. The deeper physicists move into the equations, the harder the multiverse becomes to dismiss entirely. But the more carefully they examine scientific methodology itself, the harder it becomes to accept untestable infinities without hesitation. These tensions do not reflect intellectual failure. They reflect a frontier. Physics has entered regions where mathematics advances faster than instrumentation, while philosophy struggles to keep pace with both. The result is not consensus but oscillation, brilliant people revising positions repeatedly as new implications emerge from old equations. And perhaps that uncertainty is itself important. Science at the edge rarely looks clean while it is happening. Long before a scientific idea is accepted or rejected mathematically, it passes through something quieter and far more human. Institutions, careers, habits of thought, entire generations trained to interpret reality through one stable, conceptual lens. The multiverse entered physics, carrying all of that resistance against it. Inside modern science, reputations are built through precise predictions that experiments can verify cleanly. Funding follows measurable progress. Journals reward frameworks that generate calculable outcomes within manageable boundaries. But the multiverse strains those boundaries immediately. A sufficiently large ensemble of universes can absorb almost any observation somewhere within its structure. To many physicists, this creates a dangerous problem. If every possible outcome exists somewhere, then what exactly has the theory predicted specifically? The concern is methodological, not emotional. Science depends on falsifiability, meaning a theory must risk being wrong in principle. A framework that accommodates every result appears, at first glance, to evade that risk entirely. Young researchers understand this instinctively. Building a career around controversial, difficult to test cosmology can become professionally hazardous very quickly. So caution accumulates. But beneath the institutional resistance sits something deeper, harder to quantify, and perhaps impossible to remove completely from human thinking. Each major expansion of cosmic scale has displaced us further from significance. First, Earth lost its central position. Then the solar system became one ordinary system among billions inside the Milky Way. By the late 20th century, astronomers realized our galaxy itself was only one among roughly 2 trillion scattered across the observable cosmos. Now comes another displacement. Not merely that we occupy no special location within the universe, but that our entire universe may itself be statistically ordinary inside a vastly larger structure beyond observation. That shift carries psychological weight. Thomas Kuhn described similar patterns in his 1962 book on scientific revolutions. Existing paradigms survive partly because entire professional cultures organize themselves around them. Textbooks, departments, grant structures, and reputations all become intertwined with one accepted framework of interpretation. Changing the equations is difficult. Changing the intellectual culture surrounding the equations is slower still. The Copenhagen interpretation benefited enormously from this stability throughout the 20th century. It allowed physicists to calculate outcomes with extraordinary precision while postponing deeper questions about what quantum mechanics actually implied physically. Use the mathematics, avoid metaphysics. That approach proved enormously productive experimentally, but it also created an atmosphere where questioning the foundations themselves became professionally uncomfortable. Hugh Everett entered precisely that environment when he insisted the equations should be interpreted literally rather than operationally. He asked what the wavefunction meant physically. The reaction mattered. Everett was not ignored because his mathematics failed. Many senior physicists privately admitted the mathematics was elegant. The discomfort came from the implications attached to taking it seriously. Entire assumptions about reality, observation, and uniqueness began unraveling simultaneously. But scientific resistance does not necessarily indicate dishonesty or fear. Sometimes it indicates the genuine difficulty of absorbing an idea large enough to reorganize the intellectual ground beneath an entire field. Across deserts, mountaintops, underground tunnels, and orbital design labs, a quiet race is underway. Not a race to prove the multiverse directly, at least not yet. A race to push observation far enough that certain possibilities finally become impossible to ignore. The most immediate battleground is the oldest light in existence. High in Chile's Atacama Desert, more than 5,000 meters above sea level, the Simons Observatory has begun operating with instruments sensitive enough to map tiny polarization patterns inside the cosmic microwave background. Polarization means the directional orientation of light waves. a faint structural fingerprint left behind by processes in the early universe. The measurements are extraordinarily delicate. Temperature variations in the CMB already reach precision near 1 part in 100,000. The new observatories aim to probe fluctuations even smaller, searching for circular anomalies, asymmetries, and statistical distortions consistent with ancient bubble universe collisions. But the Simons Observatory is only the beginning. Its planned successor, CMB S4, expected during the early 2030s, will combine telescopes across multiple continents into the most precise cosmological survey ever attempted. If the cold spot truly carries the geometry predicted by eternal inflation models, these instruments may finally clarify whether the pattern is statistical noise or a physical scar. At the same time, another detector is being prepared far above Earth itself. The European Space Agency's LISA mission, short for Laser Interferometer Space Antenna, will position 3 spacecraft millions of kilometers apart in triangular formation around the Sunday. Their purpose is to detect gravitational waves, ripples in spacetime itself, with sensitivities impossible on Earth. These waves carry ancient information. Some may originate from inflation, the violent expansion thought to have occurred less than 1 trillionth of a trillionth of a trillionth of a second after the Big Bang. Hawking and Hertog's final model predicts a specific primordial wave structure if the multiverse possesses finite boundaries rather than infinite randomness. A measurable pattern would matter enormously. Meanwhile, laboratories in Europe and Asia continue scaling quantum superposition experiments toward larger and larger objects. Researchers at the University of Vienna are attempting to place particles approaching nanogram scales into coherent superposition states. Nanograms sound tiny. They are. But at quantum scales, this approaches almost unimaginable size. If superposition survives at those masses without collapse, competing interpretations of quantum mechanics narrow dramatically. Some collapse theories predict failure beyond certain thresholds. Many worlds does not. Particle physics continues pressing forward as well. CERN has proposed the Future Circular Collider, a machine roughly 100 kilometers in circumference, capable of energies far beyond the current Large Hadron Collider. If extra dimensions exist at accessible scales, missing energy signatures or new resonance patterns should eventually appear. Or they will not. That distinction matters scientifically. None of these experiments alone would prove the multiverse outright. Physics rarely works through single moments of certainty. Evidence accumulates gradually, across independent measurements converging toward one explanation more naturally than others. The question remains open. But for the first time in history, humanity is building instruments specifically capable of pressing against the edge of it. Late at night, after the mathematics settles into silence, the multiverse leaves physics and begins touching something more intimate. Not stars, not inflation, not detectors buried underground. You. Consciousness remains one of the deepest, unresolved problems in science. Neuroscience can map electrical activity across the brain with extraordinary precision. It can identify regions associated with language, memory, vision, and emotion. But no equation explains why physical matter should produce subjective experience at all. Why should atoms arranged in one particular structure feel like anything from the inside? No accepted answer exists. But under many worlds, the question becomes stranger still. Every moment of awareness unfolds inside a branching quantum structure that never fully collapses into one singular path. Your brain depends on microscopic physical events constantly. Neurons communicate through electrochemical signals. Tiny charged particles move through ion channels inside cell membranes. Neurotransmitters cross microscopic gaps between neurons. At those scales, quantum uncertainty never fully disappears. Different outcomes remain possible. If Everett's framework is correct, then every quantum event influencing neural activity contributes to branching histories of conscious experience. Versions of you emerge continuously, separated by tiny differences accumulating across time. Most of those differences begin almost invisibly. A slightly altered hesitation before speaking, a different word chosen during a conversation, a brief memory surfacing instead of another, small divergences spreading gradually outward through entire lives. Philosopher Derek Parfit approached something close to this decades earlier, though without invoking quantum theory directly. He argued personal identity is not a fixed object moving unchanged through time. The self, in his view, resembles a continuity of connected mental patterns rather than a singular permanent essence. Many worlds gives that idea physical structure. You are not one unbroken line. You are a branching process, a constantly dividing network of conscious continuities, each inheriting memories from earlier versions while drifting into different futures. And every branch feels original from within. The version of you that chose differently this morning remembers the same childhood, the same fears, the same private thoughts. That version feels just as continuous and authentic as you do now. There is no privileged branch marked real. That instinct remains difficult for the human mind because consciousness feels singular from the inside. We experience one stream of awareness, not an expanding tree of simultaneous selves. But decoherence isolates the branches almost instantly, preventing any awareness of neighboring outcomes. The separation becomes complete. But this framework does not make decisions meaningless, as critics sometimes claim. Quite the opposite. Under many worlds, every meaningful possibility permitted by physics unfolds somewhere within the branching structure of reality. Nothing is erased. The branch where compassion prevailed continues. The branch shaped by anger continues too. Each becomes physically real, permanently embedded within the expanding wavefunction of the universe. And perhaps that is the unsettling part. Not that alternate versions of you might exist, but that reality may preserve every possible expression of what you could become without selecting a single final answer about who the real you ever was. Imagine adjusting the universe the way you might adjust a dial on an old radio, slowly, almost carelessly. Increase one force slightly, reduce another by only a fraction. The equations remain stable for a moment, then structure itself begins disappearing. The balance governing our universe is astonishingly narrow. Gravity, for example, is the weakest known fundamental force, yet its exact strength shapes the lifespan of every star. If gravity were roughly 10% stronger, gas clouds would collapse much more violently during star formation. Stars would ignite quickly, but they would also burn through nuclear fuel at catastrophic rates, exhausting themselves in millions or even thousands of years instead of billions. Heavy elements might still form briefly, but stable planetary systems would struggle to survive long enough for complex chemistry to emerge. A slightly weaker gravitational constant creates different problems. Matter would disperse too easily. Galaxies might never condense at all. Electromagnetism is even more delicate. Reduce the electromagnetic force by approximately 4%, and electrons can no longer maintain stable orbital relationships around atomic nuclei. Atoms become fragile. Molecules fail to assemble consistently. Chemistry, meaning the structured interaction between atoms effectively disappears. No chemistry, no complexity. The strong nuclear force sits on another razor's edge. This force binds protons and neutrons together inside atomic nuclei. Decrease it by around 2%, and multi-proton nuclei become unstable. Hydrogen survives. Almost everything heavier does not. The periodic table collapses into simplicity. Increase dark energy significantly, and another kind of emptiness appears. Dark energy drives cosmic expansion. In our universe, it operates gently enough that gravity can still gather matter into galaxies before expansion dominates large scales. But multiply dark energy by 10. Space expands too rapidly for stars or galaxies to form. Matter spreads thinly through an eternally growing void, smooth and nearly structureless across unimaginable distances. At first glance, these constraints seem almost suspiciously precise. But physicists, studying fine-tuning caution against drawing conclusions too quickly, Fred Adams and other theorists have explored whether radically different universes might still permit unexpected forms of structure under alternative physical conditions. Different quark masses, for example, could generate stable atoms unlike anything in our chemistry. Quarks are the fundamental particles composing protons and neutrons. Altering their masses changes the behavior of atomic nuclei entirely. The resulting matter might not resemble carbon chemistry at all. No water, no DNA, no familiar stars, but perhaps some other stable complexity emerges anyway, operating through principles our universe never explores because our constants prevent them from existing here. Physics does not currently rule that possibility out, and consciousness complicates the question further. We do not know whether awareness depends specifically on carbon, liquid water, oxygen, or even biological evolution as we understand it. We only know those conditions produced consciousness once, here. That limitation matters. When we imagine lifeless universes, we may simply be imagining universes incompatible with us specifically. Silence is not proof of emptiness. A universe can remain physically rich while being permanently inaccessible to the forms of perception our chemistry allows. And naturally, we could only ever awaken inside one of the rare universes where awakening was possible at all. In quiet moments of reflection, physics circles back to something almost unsettling in its simplicity, not a paradox of particles or a conflict of forces, but a question about language itself. Why should mathematics, a system invented in the mind, describe the fabric of reality so precisely? Eugene Wigner posed this question in 1960, calling it the unreasonable effectiveness of mathematics in the natural sciences. His point was not rhetorical. Mathematics, as it is practiced, often begins as pure abstraction. It is developed without any commitment to physical interpretation. Numbers, structures, and relationships are explored for internal consistency alone. Yet again and again, these abstract constructs become the exact tools needed to describe the physical world. The pattern is consistent across history. Complex numbers, originally treated as impossible or meaningless extensions of ordinary arithmetic, later became essential in quantum mechanics. They describe wave functions, the mathematical objects encoding all possible outcomes of a quantum system. Non-Euclidean geometry followed a similar path. Developed in the 19th century as a logical exploration of curved spaces, it eventually became the foundation of Einstein's general relativity, where spacetime itself is curved by mass and energy. Group theory, once considered abstract algebraic structure, now underlies the standard model of particle physics, organizing every known fundamental particle into precise symmetry patterns. Each discovery feels less like invention and more like recognition, but no consensus exists on why this happens. One radical interpretation comes from physicist Max Tegmark, known as the mathematical universe hypothesis. In this view, mathematics is not merely a descriptive tool, it is the ontology of reality itself. All mathematically consistent structures exist physically, not metaphorically, literally. Under this framework, the universe we inhabit is not described by mathematics. It is a particular mathematical structure among an enormous space of all consistent structures. Physical existence and mathematical existence become identical. The effectiveness, Wigner observed, is no longer mysterious. It becomes inevitable. We find mathematics so perfectly matched to reality because there is no separation between the two. We are not using mathematics to describe the universe from the outside. We are embedded within a structure that is mathematical in its essence. From that perspective, the success of physics is not surprising at all. It is expected. But this interpretation carries consequences that stretch beyond science into philosophy. If every mathematically consistent structure exists, then the space of reality contains not just variations of physical law, but every logically coherent system that can be expressed in mathematical form. Every consistent story has a place. Somewhere in that vast landscape, every possible configuration of laws, particles, histories, and outcomes is realized, not as possibility waiting to happen, but as something already existing in a form as real as our own. This is the most expansive version of the multiverse proposed so far, and it remains almost entirely beyond experimental reach. Yet, it reframes Wigner's original mystery in a different way, not as a question of why mathematics fits the universe so well, but as a recognition that there was never anything to fit at all. At the edge of modern cosmology lies an idea that begins not with speculation, but with simple geometry extended far beyond intuition. If space is infinite, and if matter is distributed in a statistically uniform way, then patterns must repeat, not approximately, exactly. In an infinite expanse governed by the same physical laws everywhere, every possible arrangement of particles within a finite volume must eventually occur again, not because it is likely in any single region, but because the number of regions is without bound. Max Tegmark formalized this implication with a striking calculation. He estimated the distance to the nearest identical copy of our observable universe as roughly 10 to the power of 10 to the power of 28 meters. A number so large it defies physical imagination, yet still emerges from standard assumptions in cosmology. The logic behind it is straightforward, even if the consequence is not. Within any finite region, like our observable universe, there are a finite number of quantum states consistent with physics. If space extends infinitely, then those states must repeat eventually, simply because there are more regions than possible configurations. At that calculated distance, one would find a region of space indistinguishable from our own in every measurable way. A star identical to the Sunday, a planet identical to Earth, a history unfolding in perfect correspondence with ours, a version of you sitting in a similar moment, reading similar words, experiencing identical thoughts, not similar in broad structure, identical down to every particle configuration and every neural state. But the repetition does not stop there. Farther still, at distances described by 10 to the power of 10 to the power of 10 to the power of 28 meters, the combinatorial possibilities expand into every variation allowed by physics. Every decision that could have been made differently is made differently somewhere. Every alternative life exists in full detail. Each version is as complete as this one. Each is isolated beyond causal contact. No signal, no light, no influence of any kind can traverse those separations. The speed of light imposes a limit, not just on communication, but on connection itself. And yet, under the assumptions of infinite space, they are not hypothetical constructs. They are physical regions of the same universe. There is no boundary separating reality from imitation, only distance stretching beyond any observational horizon. What distinguishes these copies from us is not their composition, but their inaccessibility. This produces a tension in interpretation. On one hand, the idea is almost emotionally overwhelming. It suggests that every possible version of a life is being lived somewhere, fully realized, never intersecting. On the other hand, nothing in the mathematics allows us to dismiss it without altering the underlying cosmological assumptions that generate it. Both intuitions persist simultaneously. We cannot observe these copies. We cannot test them directly. Yet their existence follows from extending the simplest models of space beyond the region we can see. And so, cosmology reaches an unusual position, a universe that, under its most conservative assumptions, contains not just one history, but an unending repetition of histories scattered across distances so vast they dissolve ordinary meaning of far away. At the end of all these layers of theory, calculation, and possibility, physics returns you to a single, unresolved position. You are here, not in a general universe, not in a randomly selected region of abstract space, but in this exact configuration of matter, energy, history, and time, experiencing this exact moment of awareness. The question that remains is deceptively simple. Why this universe? Not why any universe exists at all. That question has been distributed across inflation, quantum mechanics, and mathematical frameworks that all, in different ways, allow for multiplicity. The deeper question is narrower and more difficult. Why this particular realization of everything? Why these constants? Why these laws? Why this sequence of cosmic history leading to conscious observers appearing at this stage of cosmic evolution? The anthropic response begins from a constraint. Observers can only exist in universes that permit observers. This means any act of observation is automatically biased toward environments capable of producing observation. In that sense, selection is unavoidable. The reasoning folds back on itself until cause and perspective become indistinguishable. It does not explain the universe. It explains why explanation is limited. But other frameworks attempt to go further. Lee Smolin's cosmological natural selection suggests that universes reproduce through black holes, each new universe inheriting slightly varied physical constants. Over vast chains of cosmic generations, selection favors universes that produce more black holes, and those tend to also produce long-lived stars and complex structure. Under that view, your universe is not accidental. It is the product of deep evolutionary pressure across countless unseen predecessor universes. Still, it does not answer why the process exists at all. Then there is Tegmark's radical mathematical interpretation. In that framework, every mathematically consistent structure exists physically. Your universe is not chosen or favored. It is simply one of an infinite ensemble of consistent realities. Asking why you are in this one is no different from asking why you are yourself, rather than some other logically possible version of you. There is no external selector, only existence across all consistent possibilities. None of these answers resolves the discomfort completely. Each reframes the question, pushes it into a different conceptual space, and leaves behind a residual mystery that refuses simplification. But something consistent remains across all of them. The universe does not appear designed to align with human expectations of clarity or simplicity. Instead, it expands every attempt at explanation into something larger than the intuition that began it. And yet it allows those attempts. It produces minds capable of asking why anything is the way it is, even if the answer always exceeds the scale of the question that asked it. Across 4 centuries of modern science, this pattern has repeated without exception. Each time the fundamental structure of reality is probed more deeply, the result is not closure, but expansion into something less familiar than before. And so the final position is not certainty, it is continuity, the ability to keep asking, even as every answer shifts the ground beneath what asking itself means, until the question, why this universe, becomes less a demand for explanation and more a description of the fact that there is a universe here at all. There is a point in every map where ink runs out, not because the territory ends, but because representation fails to keep pace with what might still be there. At that boundary, knowledge stops being accumulation and becomes orientation, a way of holding direction without certainty of arrival. Physics has reached versions of that edge before. Newton's universe once appeared complete, a closed system of forces acting on objects in absolute space and time. It worked with extraordinary precision until it failed at high speeds and strong gravity. Maxwell's equations unified electricity and magnetism into a single field, then immediately pointed toward phenomena they could not yet describe. Even in 1900, Lord Kelvin reportedly suggested that physics was nearly finished. Within 2 years, quantum theory began to rewrite the foundations of matter itself. The pattern is not collapse, it is expansion. Each framework closes one domain of uncertainty while revealing another that was invisible until the previous one stabilized. Classical mechanics gives way to relativity. Relativity gives way to quantum mechanics. Quantum mechanics now presses against questions it cannot resolve about measurement, observation, and the structure of reality itself. And at that frontier, the multiverse appears not as an invention, but as a mathematical consequence that resists removal. But this is not a comfortable position for science to occupy. It is a place where prediction outruns verification, where equations remain internally consistent while experimental confirmation lags far behind. The detection of gravitational waves required nearly 100 years after Einstein first described them in 1916. The cosmic microwave background was predicted in 1948, then discovered accidentally in 1965 when a persistent signal in a Bell Labs antenna was initially mistaken for thermal noise from pigeon contamination. The Higgs field was proposed in 1964 and confirmed nearly half a century later at the Large Hadron Collider. Each case followed the same structure: theory first, instrument later, confirmation long after both. The multiverse may be in one of those waiting periods now, a framework already mathematically articulated but not yet fully testable in practice. Future observatories, deeper CMB mapping, gravitational wave detectors, and high-energy colliders may eventually decide whether its signatures are real or absent, or it may turn out to be something else entirely. A mathematically consistent structure with no physical counterpart, a description that fits within logic but not within nature as we can ever access it. beautiful in formulation, coherent in structure, and ultimately ungrounded in observation. Both possibilities remain open. What defines science at this boundary is not resolution, but discipline. The ability to hold competing interpretations without forcing premature closure, to remain inside uncertainty without collapsing it into narrative simplicity. At the edge of the map, certainty is no longer the goal. Orientation is, and the map continues only because we keep drawing it forward, one equation, one observation, one unanswered implication at a time, into regions where the shape of reality is still being negotiated between mathematics and what the universe allows us to see. Everything that exists around you tonight begins in deep time. The carbon in your breath was forged in a star that collapsed long before Earth had a name. The iron in your blood was assembled in a supernova that scattered matter across interstellar space more than 4 billion years before oceans existed. Even the calcium in your bones is a remnant of ancient stellar furnaces, recycled through generations of cosmic destruction and renewal. That material did not stay still. It became structure, it became chemistry, it became biology, it became a nervous system capable of tracking its own existence across time. And somewhere inside that chain, physics introduces a strangeness that never resolves cleanly into intuition. Every interaction between particles follows quantum rules, where outcomes are not singular but distributed across possibilities. In some frameworks, each interaction branches reality into multiple histories, each equally consistent with the underlying mathematics. This process does not slow down, it does not pause. It occurs continuously within every atom that composes you. Right now, in every moment of existence, reality may be unfolding as one world or many. There is no experimental consensus that settles it. The most advanced mathematical descriptions remain compatible with both interpretations, and the evidence does not collapse cleanly in either direction. But both possibilities contain the same underlying fact that anything exists at all. A universe with stable laws, a universe capable of producing matter, structure, chemistry, life, memory, and reflection. A universe that evolves to the point where part of it becomes aware enough to ask what it is part of. That sequence, regardless of how many layers of reality underlie it, is not ordinary in any meaningful sense. It is the kind of outcome that does not repeat itself in everyday intuition, even if it repeats across cosmic scales or across branches of a wave function. Hugh Everett's formulation remains mathematically intact. The cosmic microwave background still carries its unexplained features. The predictions that matched observations still match. The experiments that challenge intuition still behave exactly as they did when first performed. Nothing in the underlying data has shifted while these questions remain open. Only the interpretations compete, and new instruments continue to extend what can be measured. New detectors refine what can be inferred. New generations of experiments will eventually reduce uncertainty in ways that cannot yet be fully anticipated. At some point, a result will arrive that does not simply answer an old question, but reshapes the structure of what counts as a question in the first place. Until then, you are positioned inside the interval where physics is still incomplete, but not silent. In whatever formulation of reality is correct, this moment is happening from the inside, not as abstraction, but as experience encoded in matter that once belonged to stars. Something assembled itself from that matter and became aware enough to wonder about the assembly. That fact holds regardless of interpretation. It holds across every framework discussed so far. It does not depend on whether the universe is singular, branching, or part of something larger still. It only depends on the existence of observation. The rest is still in motion.